Okay, so we know that the derivative is the rate of change of the function. It's the slope of the tangent line at a given point. So we can find a general derivative, and that is the rate of change. We can find the slope at a specific point, and that is the slope of the tangent line, okay, the value of the derivative at a given point. Does the antiderivative have any physical meaning that we can use in solving problems? Does the antiderivative have anything that maybe will help us understand it or to make it useful to us as a problem-solving tool? Well, it has two things. Number one, it is the inverse of the derivative. And that's really handy, especially if you go much further in calculus. But it also has a really cool property. Okay? The antiderivative is the area under the curve antiderivative is the area under the curve. So, what does that mean for us? Well, if I give you a cost function, right? That cost function is going to tell you the cost of producing a product at a given moment in time. Okay? The antiderivative of that cost function will be the total cost. That'll be the total cost. Okay? But unfortunately, this kind of implies infinite bounds, and we don't really want to do that. We want to go from point A to point B, and so we'll show that like this, from point A to point B. Okay? So that notation there, right, is the antiderivative from point A to point B. Okay, so 0 to 10 would be an example. That's the total cost producing 0 to 10 units. Okay, so 1 unit plus 2 units plus 3 units plus 4 units plus 5 units, etc., etc., etc. Okay, I'll give you another example. The area under the power function. Okay, so if I had a function that defined how much power I was using, that's going to be the work done, the total work done by that power. Okay, the area under the velocity function is going to be the distance traveled. Okay, it's going to be the distance traveled. Okay, so now the question is, how do we find this area? Okay, there's a couple of techniques. We're going to start with a real simple one. Okay, real simple one. It's called a Riemann sum. A Riemann sum. And we're going to use Riemann sums to find these areas. Now, there are 4 types of Riemann sums. We're going to focus on 2 because this is based on brief calculus or business calculus. So we're going to focus on 2, but I'm going to show you all 4. And if you're in calculus 1, you're going to actually do all 4. So there's 1, there's 2, there's 3, and there's 4. Okay? And I'm going to give you a curve for each one of these XY axes. Okay, so I'm going to give you a curve for each one of these XY axes. So we're going to start here and go like that. I'm going to start here and go like that for every one of these. We're just going to kind of repeat this over and over and over. Okay, now here's how the Riemann sum is going to work. The Riemann sum is going to use rectangles. Okay, so it's going to use rectangles to help us estimate the area between this curve and the x-axis, okay? And so what we do is we make little bars, okay? And to show you how uncreative math people are, this is a left hand Riemann sum. And we would abbreviate this LHS, a left-handed sum. Why? Because the left side of the bar touches the curve. Okay. Now, something like that, if the curve kept going, right? Something like that. And this is a right hand Riemann sum, and we abbreviate it RHS, a right-handed sum, because the right side of the bar touches the curve. Now, for an increasing function, a left-hand sum will be an underestimate. For an increasing function, a right-handed sum will be an overestimate because you've got these extra pieces here, okay? And then we've got what they call a central Riemann sum. Okay, in a central Riemann sum, we actually put the center of the bar on the curve. Okay, so we put the center of the bar on the curve. Okay, so we'll see boom, 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 the center. This is a better estimate, okay? And that would be a central sum, okay? This is a much better estimate than a left or a right-hand sum. Why? Because you get a little overestimate over here and a little underestimate over here, and the idea is that hopefully those two basically cancel each other out, okay? So that's a central Riemann sum. And then the last one, we actually use 2 points, and we draw a trapezoid. Okay, and this would be trapezoidal. A trapezoidal Riemann sum. In Calculus 1, you would be required to do at least these 3, usually all 4. Because this is business calculus or brief calculus, we're only going to do left-hand and right-hand Riemann sums. Now, a Riemann sum has a mathematical representation, okay? So a Riemann sum would be written as follows. It would have this mathematical notation, and it would say something like this: I equals 1 to n f of x sub I delta x. Okay? And I'm going to flip to the next page and explain this notation to you. But that is the mathematical notation for a Riemann sum. So let's unpack all of this and see if we can understand what it means. Okay? So we'll flip over the page here. I'll write a little bigger. So we get this big E-looking thing, right? I equals 1 to n f of x sub I delta x. So let's unpack all of this. Okay, first, this is the Greek capital letter sigma, and it stands for summation. Okay, so it means we're going to add a bunch of stuff. That's all it means. Okay. I equals 1 to n. This is the number of rectangles in your Riemann sum. So if this goes 1 to 5, you have 5 rectangles. So start with rectangle number 1 and go to rectangle number 5. That's what that means. Now this, you got to remember from algebra, f of x is simply the y value of a function. Okay? So this is the y value of a function, which in our case, if you look at our pictures, is equal to what? The height of each bar. Okay? So when you're given a function, if you plug in the correct x value, that's going to give you the height of the bar. And then delta x is going to be the width of each bar. Okay? It's going to be the width of each bar. And everything we do, in this class, the width of each bar will be the same. And so, if I gave you, let's just take an example, if I gave you summation I equals 1 to 4, right, something like that, and somewhere else you knew that f of x was, let's just say, 5x, okay, and delta x was, let's say, 1. What this turns into is 5 times 1, that's this part, so 5x, and let's make delta x something different. Let's make delta x 2. Okay, let's make delta x 2. Okay, and let's make this go up to, well, let's just leave it at 4. Okay, so we're going to have 4 bars, and delta x is 2. Okay, so we start at 1. Okay, 5 times 1 times 2. That's height times width. That's the area of the rectangle. Plus our second interval, right, would be what? 5 times 2 times 2. Height times width. Plus 5 times 2 times 3 times 2, right? And so we keep going. The height changes every time. Why does the height change every time? Because we're dealing with a curve, right? So the height is going to change every time. But the width of each bar should be equal. Should be, hopefully, right? That's what we hope for. We hope for nice equal bars. Okay? So that's all that means. So we're going to come back, we're going to try a few examples with this, and I'll walk you through it. It's not that confusing. Don't let it bother you. But really, it's just turning this into an addition sentence. So it's going to be the height of the bar times the width of the bar, and if n is 4, then you're going to have 1, 2, 3, 4 components to add together. Okay? So we'll come back, we'll try a few examples, and if you have any questions about this video, let me know.